So you're gonna see, I have like a captive audience with y'all. You're gonna see, like it or not, some pictures I've taken of the Milky Way, and they don't do it justice. A lot of times, astronomy photos don't do it justice. There we go. I think that's what I want. Road trip. Okay. So, what do you think? Just a minute ago, we saw a picture of a guy seeing the Milky Way behind him. Oh, by the way, I brought this as a prop for the Milky Way. Okay, so I don't have a Frisbee, but a lot of flatness going to them. The Milky Way galaxy kind of has a flatness to it. What's the diameter from side to side? 100,000 light years, yep. What's in the center? Black hole, supermassive black hole, exactly. Sometimes we see galaxies like this, sometimes we see galaxies like this, sometimes we see them kind of tilted. So we are about halfway between the center and the edge. So that makes us what, about 25,000 light years, I think, or so, from the edge and from the supermassive black hole in the center of our galaxy. So when we look at the Milky Way, basically we are looking into kind of the plane. We are here and we're kind of looking outward. So the way this would go is we are here looking that way. Do you know what I'm saying? And in a given night, actually, if you look up and around, you'll see what's called the Milky Way, which is looking into the Milky Way galaxy. Well, this is what I started saying. This is kind of stepping out. Can you kind of see a little bit of spiralness to that? Okay. These are all not stars. These are all galaxies in and of themselves. Now, I would almost kind of hesitate to show you this picture because like last night when we looked out, we saw a bunch of stars. We saw some constellations. Okay, so most of the things that are giving off light in our nighttime sky are just beautiful stars, Star clusters. These things we call nebula, which is kind of just a gas in outer space, which probably has a star somewhere in it, a nebula. But these are other galaxies. Okay, so these are other galaxies. So these are much farther than the stars. Okay, so you really can't see with your naked eye this. The only thing, do you remember, starts with letter A, which galaxy can you see with your naked eye? Andromeda galaxy, yes. You can see Andromeda galaxy. So I said that we kind of have this address thing going. We are on the Earth. We kind of go back and forth here, aren't we? We're on the Earth. The Earth is part of the sun's solar system. Our sun is a part of the Milky Way galaxy. And then I don't know if you remember, but I said actually galaxies are kind of grouped together in what we call galaxy clusters. We're part of the local group, like everybody knows your name. And then clusters of galaxies are grouped into superclusters of galaxies. I just think that's funny, clusters and superclusters. You're like, really? Could you not come up with another name? So they're kind of more organized than you might think. So I'm going to dim the lights. This is a photograph I took, okay? And what do you think? Is this a galaxy like this? This is A, or is this a galaxy like this? B. How many people think it's A? How many people think it's B? Yeah. So this is, I think, called the Whale Galaxy. Now, just that telescope I had out last night, that's what I took this through. Just looking in this area, I would barely maybe even make something out, just barely. But when I go ahead and set my camera settings to, I don't know, maybe 3 minutes to gather the light, this is what I see. That's one of the things I like about photography through my telescope, because it's like, I don't see it, but then you like set it for a long time, and you're like, I see it. You don't need a telescope to play with that, dang. You can go out at night and somehow mess with your camera and make it like a 3-minute exposure, and you can see all sorts of things that you can't see with your naked eye because it's gathering the light. So this is another one. I think this is the triplet in the constellation Leo. This fuzzy little thing, fuzzy little thing, fuzzy little thing. I know, you're like, really, Mrs. Snipes? But it's just kind of fun. And then this one, what do you think? Is this one like this, or is this one like this? How many people think it's the A? Me too. So you kind of see the wispiness to it. And this is the big daddy of them all. This is Andromeda. This is M31. M31 actually has, it's about the same size as our galaxy. If you've heard, oh my gosh, our galaxy, the Milky Way, is going to run into another galaxy one of these days, they are actually on a collision course. Okay, I'll be long gone when that time comes. But yeah, the Frisbees are coming closer and closer together. And guess what? It has a supermassive black hole. We've got a supermassive black hole. It's kind of the Brady Bunch, you know? So, yeah, when they join, and we see this in other galaxies, when they join, they'll make one big supermassive black hole. Okay? Yeah.
Okay, so in again, like, yeah, in the universe, the planets rotate because of the gravitational pull of the sun. But what causes the galaxies to move?
Oh wow, you just jumped clear to Unit 5 in here. Have you ever heard of dark matter? Yeah. Actually, the way, and if I had 2 planes, the way that
Boom.
I know, you're right.
Look at this.
So the way that these interact, actually, we can use Isaac Newton's laws of motion to understand the distribution of mass based upon how we see these guys interacting. Heck, even how, like, within the galaxies, the motion of the stars within the galaxies, we can use Newton's laws again to understand how the mass is distributed amongst those stars. Okay, so it's observations, then we get to mass. So mass is kind of that missing link. And I say dark matter or dark mass because honestly, the visible light that we see can't account for all of that. And one of the things that that cosmologists or astrophysicists know is that kind of strewn between these galaxies is dark matter. So, okay. So, good question. So the last couple of slides look at, one of the things we're going to talk about is I usually use the word unfolding of our universe. Now remember, these are galaxies, right, with like 100 billion stars in each galaxy. And there's, what did I say, 2 trillion? Oh no, but there's a lot of galaxies in our observable universe. So then galaxy, 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 galaxy. And all that stuff used to be into one little tiny point called singularity. The thing about singularity, we'll talk more about the Big Bang, the thing about this thing we call singularity, is that if you step outside singularity, there's no space, there's no time. It's almost like a Doctor Who sort of thing, okay? And then Big Bang, short, wasn't loud, but anyway, and then it created, as it moved out, so this is the universe moving out in all directions. As it moved out, it created space, and I know we don't usually link time with space, but it created the fabric of what we call space and time, okay? So fast forward about 15 billion years later, and the universe is as we see it. The universe is as we see it. But remember, we talked about if you look back, if you look at an object that's way far away, you're looking at that object as it was that long ago. So we can actually kind of look at baby pictures. So I know that's a lot. I wanted to bring that up because we're talking about 14, 15 billion years old. So if we kind of think of today is, who doesn't love New Year's Eve? I mean, well, actually, I don't know. New Year's Eve, it can be depressing. I don't know. It can be fun, depressing. So now I think about it, I don't know if I love New Year's Eve. So anyway, but if you think about that magical time when it's about ready to go from December 31st at 11:59 to the new year, it is kind of exciting, I guess. All sorts of emotions. That's now, okay? Then if you go ahead and say, well, January at midnight was the Big Bang, okay? And then you go ahead and divvy it up for what the life of our universe was. This is what you come up with. So here we have January 1st, midnight, Big Bang. February, so January, February, a month later, the Milky Way galaxy comes into being. Then September 3rd, oh my gosh. So what do you think? February to September 3rd. we got some time there. And we're going to be talking kind of about a little bit about what happened between that gap. But September 3rd would be, let's see, I can't read that slide. Earth forms. September 22nd. By the way, when Earth formed, we'll talk more about that too. So I brought her here. If this is this is our sun. We say Earth formed basically when the sun turned on. So basically, the solar system kind of what we say kind of came to life about the same time, about 4.6 billion years ago. With the B also, you have to be careful with your B's and your M's. So about 4.6 billion years ago, sun turned on, then Earth was kind of what it's going to be. So that would have been September 22nd. And then we go on to December 17th. Is that dinosaurs? Yep. Nope, yeah, Cambrian explosion. That's not the dinosaurs, is it? It's something else. Not biology. Cambrian explosion, December 26th, rise of the dinosaurs. December 30th, extinction of the dinosaurs. Right, so we're here, remember we're the 31st on the verge of midnight. And then the 31st, 9 p.m., early hominids. 11:58 p.m., modern humans. 25 seconds ago, agriculture. 11 seconds ago, pyramids. Who doesn't love pyramids? And then 1 second ago, Kepler, Galileo were doing their thing. And then now is now. So anyway, yeah.
How can they pinpoint dates and times like that?
Well, we'll be talking, it's not just any one way. So one thing that science is good about is you throw something out there and you come at it at different angles. So we'll be talking about that, but each one of these probably has a multiple way of getting to that date, that general date. Good question. So remember that anytime you see a color ring around this slide actually came from Canvas. So where did my paper go? There it is. So we're on an assignment slide now, guys. So you guys did the first assignment. This is the second assignment. Some of you guys already have done this. Now just do your best. This is actually packing up numbers into scientific notation. If you're like, oh, you don't have no idea, well, just do your best. Okay, I'm wanting to kind of see what you can do with this. Remember, I don't have numbers in this class, but I do want us to kind of know if we see 3.5 times 10 to the 17th, you know, times 10 raised to 17th power, that's a big number. And that's kind of what I'm after here. This question here? Okay. So remember that my questions that have Q in front of them, I think that's right. Yeah, my questions that have Q in front of them, they're my questions. I came up with them because I couldn't find one in Canvas, quite frankly. Okay? So those will be due Friday. Okay. So let's take a look at the next part.
I didn't realize when I gave you my homework that there's 2 left.
Oh, okay.
But I can put them on a separate piece of paper unless that will make it confusing for you.
Either way, do you want it back or do you want separate? Okay. She was just saying that she turned in, you can turn in your homework early if you want, and she's just going to add on to her homework. And I was also talking earlier today, if you're looking for a place in Canvas to submit your lab assignments, I'm going to add that. So you could, for now, you can email them to me. That's fine. That's exciting. But for your next lab, there'll be something in Canvas to, kind of like you do your assignments, there'll be a little thing that says Lab 1, Lab 2, Lab 3, Lab 4. Okay. All right. So what do you think? What's this? It's the Milky Way again. It's beautiful. Yep. Now I've looked at enough pictures, oohed and on over enough pictures that they set this so they could get the dark picture as possible. There's a good chance if you go to this remote location, you're not going to see it that distinct unless you take a picture of it. But it might see it that distinct. This is the southern hemisphere because can you see this little thing right here? This actually is the Large Magellanic Cloud. In science, they do some things that actually get on my nerves, and this is probably one of them, okay? So those 2 circles are circling galaxies. Those are galaxies. If you're like me, well, why'd they call it a cloud? I don't know. Do you know what I'm saying? Large, and it's hard to say, Magellanic, like Magellan, large Magellanic Cloud, small Magellanic Cloud. It's on my bucket list. Because as you guys know, depending upon what hemisphere you're in, you see different stars. So it's beautiful. We'll be talking more about this too, but can you kind of see the Milky Way? So you're looking into the disk of the galaxy, and you might be like, well, I know there's stars, like, and you might be wondering why there's kind of these dark lanes. These dark lanes, actually think of those as kind of dark gas that's obscuring your ability to see the stars behind them. So it's material there, but it's just not stars. Oh, I have a friend at the observatory who just reminded me that, holy colody, if you haven't done it yet, you have a pair of telescopes, a pair of binoculars. On a dark night, you should scan the Milky Way, and there's like tons of stars with just your binoculars. You're like, I had no idea. It never gets old. I'm going to turn on some lights here. Okay. So one of the things, you're like, oh, she must be getting serious. She's turning lights. So one of the things I want to try to relate to you, and sometimes you need to kind of kick this around in your own mind, is this idea of kind of relative motions. So this is still the sun, and I brought an Earth today. Okay, so you guys know there's too many R's. This is rotation. So what direction do you think the Earth rotates? Counterclockwise, I just said. So if you're looking at the North Pole, oops, no, I was right the first time. Does that look counterclockwise to you? Okay, good. Okay, so what direction is it rotating down South Pole? Clockwise, but that's not our problem. Counterclockwise, very good. Okay, so how long does it take it to complete one rotation? 24 hours, yep. But maybe some of you guys already know this. Actually, it used to be rotate faster, and it's been slowing down ever since. So I know. And let's see, how does that work? I think it has to do with energy is conserved, and this rotation is a type of energy, but it's being transferred. It's losing some of its rotational energy.
I think it's all the fat people.
Ah, no.
So then the times that they say that things were created might actually be off a little bit then. If it went a lot faster than
years. Well, now the years are different. So this is a day, and then a year would have to be, yeah, I can see what you're
But
saying.
you know what I mean? Because if our 24 hours
Yeah, this is
slower
24 hours.
now, if it was a lot faster.
But all of the calendar I just looked at was years. And so years is, and make sure I go the right direction, counterclockwise. So yeah, does this look right? Yeah. Okay, now I am orbiting the sun. Okay, and a year would be one complete orbit. So if I come back around here, that is one Earth year. Okay, not to say that this, right now we have 365.25 days rotations in one revolution. Too many R's. One revolution and orbit are synonyms. And we used to have more days in 1 year. So yeah. So pretty good. So too many R's. So when you buy, not that you have to go out and buy one by any means, but like if you buy a globe, it usually, if they put any thought or anything into it, it's usually tilted. So a lot of times I'll bring, just grab a yardstick, and its axis that it spins on, its axis rotation is tilted. And I guarantee it's going to be on your first unit exam. That tilt is what we say is 23.5 degrees. You're like in order to get an angle of 23.5 degrees, it has to be relative to something. And I'll show you what it's relative to. So if we were to take the Earth's axis of rotation and make it like this, straight up. Straight up to what? It has to be straight up relative to what? Well, straight up or perpendicular relative to this plane that it orbits the sun on. Okay, so this is to say, and there are some planets that do this. It's all counterclockwise, right? So there are some planets that do this. Okay, notice I'm straight up and down. That's not the Earth. Okay, let me see. We got north that way, right? So for the semester, if I can remember to do it, I'm gonna go ahead and check this out. Instead of straight up and down, I'm gonna go ahead and that's my reference point. I'm gonna tilt it 23.5 degrees. Okay? Now watch. Okay, watch carefully. So I'm gonna go a year and watch my tilt. It's north. This is, let's see, if I go quarter orbit, that's what, 3 months? Okay, good. So I'm gonna go 3 months. And then I'm gonna go 3 months. 6 months from where I started. And then another 3 months, that's 9 months later. See, that's all. Yeah, that's right. Okay, so you kind of caught that. It's tilted, but it always keeps that same tilt directed towards a star we call the North Star, exactly. If you were to go dot, 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 you would hit the North Star, which we call Polaris. Yep, that's the deal. Okay. So it's tilted 23.5 degrees from being perpendicular. And you might be like, okay, so where did that tilt come in? And actually, we're going to get to that in one of our lectures, and it's kind of thought that early on in our solar system, when the planets were still forming, there was a lot of extra impactors, extra rocks, extra planet wannabes. So something perhaps the size of Mars actually hit the Earth, okay, and the Earth was still forming, and so some of the Earth actually splashed into outer space. And kids get caught this in school, because I know I hear it from kids out of the observatory. They're like, and that stuff that splashed out in space actually kind of snowballed up and became our moon. Sounds like it, but it's cool. There are different reasons why we know that's the case. One of the things is that when we went to the moon, they brought back moon rocks that are similar to the surface of the Earth. So anyway, that's that. All right? Important things here. And if you're like me and don't daydream when you drive, but sometimes I daydream about these things. I'm like, oh, that's cool. So this is kind of what I just showed you. You can kind of see the Earth's axis of rotation tilted, 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 tilted. Always the same, it's tilted the same amount, and it's always pointed the same direction. Now you might be like, well, Mrs. Snipes, right now you're pointed to that wall. Okay, right now you're pointed to this wall, and you're back to this wall, but here you're back to, you're like, well, how can it point to the same star? Because you're kind of wiggling back and forth here. And the answer to that is parallax. Okay, we're going to talk about this soon, maybe. But the farther away something is, like the North Star, like we call the North Star right now is Polaris, the farther something is, when you move this way, it doesn't change its position. Okay. But that's because it's so far away, and that's called parallax. All right. So you would say the sun rises in the east, and it appears to set in the west. Sometimes my mom, who's taught little kids, elementary students, she's like, that is so wrong. It makes the students think that the sun is actually orbiting the Earth. And I'm like, I don't know. But the reason it appears to rise in the east and set in the west is because the Earth is spinning. So sometimes I'll take a globe and I'll try to kind of have it help make sense for me. So who sees the sun first? West Coast or East Coast? East Coast, yep. So I'm going to kind of change up things. So let's see. You guys can be the sun, okay? And I'm going to go ahead and put this thing that this is where daytime and this is nighttime, because you guys are the sun, right? So what direction is the Earth spinning? Counterclockwise. Make sure I get this right, hopefully. So so we need to go. I know, we're like, dang it. Okay, so I'll go over here to Asia. All right, so counterclockwise. That's not us. That's not us. Okay, you guys are the sun. So just like you told me, who's getting to see dawn? East Coast. And so what time zone do we call that? Eastern, very good. That's Eastern's got dawn. Who comes next? Central. Yeah, I have to concentrate. I always usually think of like the TV shows. So Eastern, Central, what comes after Central? Mountain. What comes after Mountain? Pacific. Yep. Exactly. All right. And time zones, the way they're broken up is about every 15 degrees, what we call longitude is a new time zone, about. And there's places, yeah. So anyway, so that's kind of how that works. So the Earth is spinning, and we said it right now it's 24 and a half hours to go ahead to go from dawn to dawn. Okay, so that's how that works. So that's the sun, but you guys also see that the moon also appears to rise in the east and set in the west. So let's go ahead and make you guys the sun still. Let's see if this works. You guys are the sun, of course this is the earth. What phase of the moon were we at last night? Quarter. First quarter, exactly. So I'm going to go ahead and put the moon over here for now, and that is going to be first quarter. Now the thing about the moon is, let's see, you guys are the sun. Yeah. No, I need a globe, not something flat. The moon over here, you're the sun, you're only lighting up half of the moon. Okay, so one hemisphere of the moon. Of the hemisphere of the moon, I only see actually one half of that one half. That's why it's a quarter, if that makes sense. You guys are the sun. Okay. So you guys are over here. Let's go back. This is dawn, right? We said counterclockwise. Counterclockwise. Okay. Oops, this is dawn. All right. So let's see how this works. Dawn here. Now, if I'm on the East Coast, the sun is going to appear to rise. Okay. Let's see how this works. This would be noon. Do you guys buy this? And this is sunset. Does that seem right? You're on the East Coast. I'm on the East Coast. Yep. Sunrise, noon. You guys are the sun. Sunset. Okay. Moon's right here. So here about noon, sunrise, noon. Do you see about noon that you're going to start to see the moon? About noon, the moon's going to rise.
On the
East Coast, yep. And then actually here, we're going to be at sunset. And sunset, where is the moon relative to kind of your horizon? Well, I'll kind of answer my own question. It's actually, when it's in its quarter phase, it's kind of like right overhead. And if the folks who went out last night, sunset, the moon was nice and high. Okay, then the sun is sunset, the moon was nice and high. Here we go, we're still on the East Coast, we're going nighttime, you guys can't see it. Okay, but actually the moon is gonna appear to set in the west. And actually, probably about, 3 a.m. maybe or so, it's gonna set. And then here from 3 a.m. to sunrise, we can't see the moon, that's over here.
It was crazy last night how perfectly in half, how dark it is. Instead of like it bleeding in, you would think the rays, you would see like bits and pieces, how it literally cuts it right in half like that.
Yeah. Now there's this thing called Earth. It's called Earth Shine Back to the Moon. Earth Shine Back to the Moon. And actually it does illuminate the non-illuminated part from the Earth. Yeah, and if you play around with your camera settings and kind of do an overexposure, you can see that. So it's very subtle though. It's awesome. Oh my goodness. A lot to cover here. Okay. Because another thing I want to cover, something I talked about last night, and so this is north, okay, pointing to Polaris. And actually, if you go ahead around Polaris and kind of watch the movement of stars, Polaris is a star. It's actually the end star in the Little Dipper, the handle of the Little Dipper. That's what Polaris is right now. You will see them move counterclockwise around Polaris. So Polaris is awesome, but Polaris has a couple of neat things to see in the sky. It has what I call a W, which is the constellation, starts letter C. Cassiopeia, the W is Cassiopeia, and I'm kind of thinking of what we saw last night. There's Cassiopeia, and what was over here? The Big Dipper, yeah. So everything, including these guys, go counterclockwise around Polaris. So if you have the patience, you can actually see them go like this. Okay. And then in 24 hours, they'll make one circuit. Okay.
So they move as well as when we're moving.
Well, and the reason these appear to go counterclockwise is the same reason the sun appears to move, because the Earth is spinning, the Earth is rotating, is what makes these stars move. And when I say move, sometimes students conjure up, oh my gosh, they're like scrambling. They're out. No, they stay in that cool, rigid form, okay? But they all do that counterclockwise around Polaris. One way to think of it is so I did that. So we have Cassiopeia and the Big Dipper, which is not a constellation, but an asterism. It's a sub-constellation of the Ursa Major. So if we go ahead and think that's a circle, that's a circle, that's a circle, that's a circle. Well, if I go ahead instead of north, if I'm going to kind of go east and west, what we've just then created is things rise in the east and they appear to set in the west. We've just kind of made a big old honking circle. I mean, this counterclockwise is consistent with what we see rising in the east and setting in the west. If I want to go ahead and turn around, kind of hurts my brain, but you'd see the same sort of thing coming from the east and setting in the west, coming from the east and setting in the west. So that's what your sky does because of this, just because of that. Well, that's serious. Oh, but that wasn't what I said. Okay, here's the deal about planets. What planets did we see last night? Saturn and Jupiter, exactly. Venus right now is a morning planet, I think, and so is Mars. But here's the deal. This is the sun again, and we kind of talked about how the planets all orbit the sun, okay? They actually all orbit it on a common, I know this is for my galaxy, but this also can be kind of what we call the plane that the planets orbit the sun in. Okay, they're kind of making what we're going to call it the plane of the ecliptic coming up. So here's the deal. If I go ahead and I'll make this trash can, we'll make it Jupiter. Jupiter, beautiful. Make this trash can Jupiter. And so is Jupiter closer to the sun or farther from the sun from us? It's farther from the sun. Yep. So we'll go ahead and do that. The thing about it is the farther away the planet is, the slower it moves in its orbit. And that's actually a Kepler and a Newton thing. Kepler's laws of planetary motion and Newton's laws of motion in general. So Jupiter is kind of slugging along. You might say, well, of course it takes longer because its orbit is bigger. No, honestly, not only is its orbit bigger, but it's moving more slowly in its orbit. So do you guys buy this, that? You guys told me it's outer, so we'll go ahead and this is the Earth now. So does this work for you? I'm gonna go ahead and put my day break right here. So this is daytime, this is nighttime, is that okay? Because there's the sun, you guys aren't the sun anymore, there's the sun. Okay, so as we spin around, notice that nighttime is here. So, I did that right. So here we actually can see the dragon. You can see Jupiter, right? Okay, why? Because it's called its configuration, and actually this gets into astrology a little bit, but its position relative to the Earth and Sun is its away. Well, what happens if Jupiter, and it is sometimes, oh yeah, it moves slowly, so let me move, all right? This would be what, 6 months later? Jupiter's poking around. Okay, so this is my day, daytime, nighttime. Well, can you see if I go ahead and get it right lined up? You know, here's my nighttime. Love the sky, love the sky, love the sky, love the sky. Oh, dawn, daytime, daytime, daytime. Well, can I see Jupiter? And the reason I can't see Jupiter is because the sun's in the way. Think of it that way, but when the sun is up, it actually, that light from the sun interacts with the the atmosphere and the earth, and it makes those blue skies called Rayleigh scattering. It's a phenomenon, so we can't see the stars. Is Jupiter still out there? Yeah, but the way its configuration is, we're not going to see it. So for those 6-month period, I don't know if you'll buy this, again, this is like, how does that work? So for that 6-month period, as the Earth takes 3 months here, I might still see Jupiter, okay? But Jupiter is going to actually move against the background stars. You know, the constellations we kind of know some of the names of. Jupiter is going to appear, because it's close and parallax is happening, to move against the background stars. So the name planet actually is Latin for wanderer. So I'm just amazed at the people, so many hundreds of years ago, when they didn't understand what we know about our solar system and our galaxy, not to mention our universe, and they noticed that, like, here was the set of constellations, here was a set of stars, and they would see an object wander through that. So last night somebody said, can we see Pluto? And I've had friends at the observatory. The best thing you can see for Pluto is basically as it's passing through a constellation, Pluto looks like a very dim star, and you'll see it move. She's like, I saw Pluto. I have a friend at the observatory, and I'm like, really? Did you really see Pluto? Okay. Of course, last night, what color was Jupiter and Saturn? Kind of orangish, yeah. And then Uranus, Neptune, I'll look them up to see if maybe we can catch them for our next lab on the hill. But Uranus and Neptune are blue. But they don't look as cool as the Jupiter and Saturn. Okay. So stars. You're like, the Big Dipper's the Big Dipper. Orion is Orion. I have some pictures of Orion coming up. It's pretty famous. The W, Cassiopeia, is Cassiopeia. Okay. They look like they're fixed, even when the Earth orbits the Sun, and the reason for that is that they are so far away that parallax is not an issue. We need to talk about what parallax is. Parallax only applies for things that are kind of close to you. The closer they are, the more parallax you see. We've been talking about the Milky Way. Isn't that beautiful? Yeah. Okay.
Has a constellation star ever died?
That's a good question. Yeah, the whole dying process, stars don't live forever. Ours won't live forever.
Right.
It's got about another 5 billion years life before it expands to a giant. Stars have died. It depends on the mass of the star. The coolest way they die is the supernova event, the blow up one. Okay, but they don't all go out that way. Our sun won't blow up. And then when that happens, you have to, your constellation is missing that star.
Right.
Yeah.
Is there any constellation that has a missing star that they used to have because the star died?
I would say there's no famous one. There's no smoking gun. But with that said, the observatory, my friends out there, I just love them because sometimes they get so excited about the star that died, the supernova, and I'm like, dude, it's not there anymore. But during a supernova event, we have that kind of the bright flash, which from our distance, basically, but anyway, so yeah. Good question. So this is not up yet. This is a fall Orion. When I'm circling Orion. The constellation Orion is a fall constellation. Sirius, do you guys remember what was significant about Sirius? Anything? It's the brightest, very good. Sirius is the brightest star that we can see. Sometimes called the dog star because it's part of Canis Major, which is big dog. If I do some constellations on your exams, I'll try to kind of tell you what constellations they would be. So this is a good place to stop. When we start Friday, I'm hoping to remember, because I want to actually take you to Stellarium, and we're going to kind of look at some of these motions we've been talking about. Stellarium. All right. So we have class on Friday, but do we have class on Monday?
No.